Science Fantastic with Professor Michio Kaku.
This is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And in this hour, once again, we're going to throw the lines open because this hour is your hour. Let's move right along now and take the first listener phone call.
Dave, Seattle, how do you know the universe is shaped like a bubble when we're talking about such large distances that what we actually see in the night sky is billions of years old because the light, is that old, and we don't actually see the universe as it existed billions of years ago. So how do we know what the shape of the universe is?
Well, you ask a very interesting question. First of all, it was Edwin Hubble back in the late 1920s, who took the largest telescope available at that time and analyzed what is called the red shift. So let me explain. If an object like a star emits yellow light and it is moving away from you, light is stretched as a consequence because light is a wave and is stretched like an accordion if an object that is yellow moves away from you. In other words, it becomes slightly reddish, and that's called the red shift. If a yellow light moves toward you at very fast velocity, near the speed of light, light waves are compressed in the forward direction, and it becomes slightly bluish, and that's called the blue shift. So when we look in the night sky, what do we find? We find the galaxies are almost all moving away from us. That was when Edwin Hubble realized that the universe was expanding. Now, if it's expanding, then we can begin to ask the question, well, what is the shape of the universe if we go far enough? Well, the short answer to that question is we don't know. However, by looking at supernovas that exploded billions of years ago, we can use that as what is called a standard candle. Now, one objection to Einstein's theory is that how do you know how far an object is? A headlight, for example, in a car, if it's very far away, it could be very luminous. Or if the car's light is very close to you, it could be very dim. So you could be fooled. You could be fooled in terms of judging the distance to a car because you have to compensate for the luminosity of the light bulb as well. That's why we use what are called type 2 supernova. It turns out that, to the best of our knowledge, they are the same throughout the entire universe. So this gives us a standard candle by which we can calibrate the redshift and calibrate the luminosity of these stars. And that's why we feel pretty confident that the universe is expanding. Now, we don't believe that we are the center of the universe. That's what the ancients may have thought. The ancients may have said that, well, if the universe is expanding, that we're at the center of the expansion. We don't believe that we're at the center of the universe anymore. So the universe is expanding uniformly in all directions. Any point in the universe should see the stars and galaxies moving away from them. And the simplest object that has this geometry is a bubble. Now, that doesn't mean that the universe is bubble-shaped. However, a bubble has this basic geometry that on any point on a bubble, every point, any insect, let's say, on the bubble, would claim that the objects on that bubble are moving away from you uniformly because the bubble itself has no center. And so, of course, there could be things that I just described that are incorrect. However, to the best of our knowledge, this is our understanding of what the universe itself looks like. And then the question is the universe infinite or not? We don't know. We think that the original universe had a turbocharged expansion much greater than envisioned by Einstein himself, called inflation. In fact, one of my colleagues, Alan Guth at MIT, was the physicist who proposed the inflation idea. It fits all the data points. And he may eventually win the Nobel Prize for the inflation theory. Now, the inflation theory is a quantum theory, and therefore, if it happened once, there's a certain probability it could happen again, and again, and again. And so this gets us into a multiverse theory, that the universe is not only a bubble, but it's a bubble in a bubble bath of universes. And so the universe turned out to be a lot more complicated than we originally thought. We now believe that our universe is perhaps just one in a multitude of universes, and big bangs are happening all the time. Big bangs happen when two bubbles collide, or when two bubbles fission in half to create two baby bubbles. And we think that is the Big Bang. And so sometimes people say that we physicists do not have any theories about the pre-Big Bang universe. Well, that's not true. According to string theory, which is what I work on professionally, we think that there's a multiverse of universes with Big Bangs happening all the time. So let's move on now to the next listener phone call.
My name is Dean. My question is, why can't we use a solar array in outer space and use the sun for energy? Thank you.
Well, you ask a very interesting question that actually is possible. Believe it or not, your proposal is possible. That is, why not? Why not send satellites orbiting around the Earth that have gigantic mirrors and can funnel the radiation and beam it down to the planet Earth? And so we would have basically unlimited sources of energy for free. No one's going to meter the sun. Since you can't meter the sun, it means that you can have energy for free. Also, sunlight is about 10 times brighter out there in outer space than on the planet Earth. Believe it or not, 90% of the energy of sunlight is lost as it moves through the atmosphere. It warms the atmosphere, of course, but 90% of the energy is lost. So why not have satellites in outer space? Well, there's a catch. There's always a catch someplace, right? And the catch is cost. It simply costs too much money to build these gigantic mirrors in outer space. These mirrors would have to be miles in diameter in order to make this thing economically viable. So NASA has looked into it. In fact, I've seen some of the reports. NASA has seriously looked into solar energy from outer space. It's called space solar energy. It is technically possible, but the costs are enormous. For example, it costs $10,000 to put a pound of anything into orbit. So think of a book, or think of just something that weighs, about almost a pound, and have it orbit around the planet Earth, not going to Mars or the moon, just orbiting the Earth. It costs $10,000 to put that book into orbit. And so you begin to realize that, hey, that's your weight in gold. Think about that. That's your weight in gold. So think of a gigantic solar mirror in outer space made out of solid gold, and then you can begin to realize the cost of space solar energy. So what's the key here? The key here is time. As time goes by, the cost of space travel drops. For example, Elon Musk of SpaceX wants to create a fleet of reusable rockets. He wants to drive down the cost from $10,000 a pound down to $1,000 a pound. Now think about that. Once the price of space travel drops by a factor of 10, it could literally open up the heavens for commercial use. But unfortunately, at the present time, it's still out of the question. Now, another possibility for solar energy, space solar energy, is Mars. Mars is very cold. So when we go to Mars, what's the point of staying there if you're going to freeze to death? Some people have said, well, why not? Why not put solar satellites around Mars? They would be cheaper because Mars has a lower gravitational field than the planet Earth. Why not do that? Well, okay, it's possible. That's one way to, quote, terraform Mars. But again, the question is cost. It'll take many decades to drive down the cost of space travel, but that's the killer. In fact, once we had the Apollo space program back in the 60s and 70s, we kind of lost interest in space exploration. Why? Because of cost. It simply costs too much to put payloads into outer space like a space solar satellite. Okay, let's move right on to the next listener phone call.
This is Reese. I'm wondering if you take all the resources of the world and pile them up on one tectonic plate or the other, if that causes earthquakes on the weak links. So by building structures and cities on on unregulated areas, are we actually causing earthquakes? Hey, love your books. Bye.
Well, the short answer is no. However, we have to look at the larger implications, not just of extracting oil from the underground, but actually injecting fluids down there. And this is where fracking comes in. For example, you probably noticed that the price of oil hasn't risen. In fact, it's gone down in many areas. And so nations like Venezuela and Iran that profited from the high price of oil had to suffer when the price of oil began to drop. However, fracking involves injecting large amounts of wastewater into the ground. And that, we think, is causing earthquakes. If you go to Oklahoma City, Dallas, Texas, and talk to the people there, they'll say, yeah, it's quite noticeable that there are lots of small earthquakes. And if you take a map of Oklahoma City and put an X where we have all the small earthquakes, like less than 3 on a Richter scale, and then put the areas where we have fracking and injection of wastewater, we see almost a 1-to-1 correspondence. And so the U.S. Geologic Survey, based in Menlo Park, California, a branch of the U.S. government, scientists there have said that, well, yeah, we think, we can't prove it, but we think there's a direct correlation between the injection of so much wastewater from fracking and the increase, many times in-fold increase in the frequency of earthquakes in these areas. And so, yeah, in some sense, we're now beginning to tamper with the stability of the planet Earth itself. I mean, who would have thought that we could do this? Okay, let's move right along to the next listener phone call.
Edgar, I'm from Canton, Ohio. My question is about transportation. I want to know at what point scientists have become with transportation. Are they able to transport objects, animals, or humans at this point? Thank you very much.
I think what you're mentioning is teleportation, because, of course, we can transport people and animals the old-fashioned way via trains and cars and planes. However, if you watch Star Trek, they simply push a button and zap the person's atoms and shoot the atoms across. Well, it turns out that's not possible, but we have something called quantum teleportation, which is possible. In fact, the world's record for that was set just a few weeks ago in China. Here's how it works. We're not actually dissolving Captain Kirk and sending atoms of Captain Kirk across space and then reassembling him someplace else. That's a dream. What we do is send the information contained in the atoms of Captain Kirk. That could be done using what is called quantum teleportation. Now, here's how it works. If I have 2 electrons that are vibrating in unison, and then I separate them, there is an umbilical cord, believe it or not, an invisible umbilical cord, according to the quantum theory, that connects these 2 electrons. So in some sense, they are aware of each other. Kind of bizarre. Einstein, of course, hated this idea, because if you jiggle one electron, then the other electron is in some sense aware that its partner is being jiggled, and that information travels faster than the speed of light. So Einstein said, aha, it must be fake, because information is traveling faster than the speed of light. Well, believe it or not, Einstein was actually wrong on this one. We actually can, in fact, send information using quantum teleportation and what is called entanglement. So what's the status? The status right now is that we can send atoms of cesium and rubidium, the information contained in these atoms across many, many miles. In fact, one day we'll send it into outer space, perhaps to the moon, perhaps even Mars. Now, what's the catch? There are several catches here. First of all, we're not actually sending atoms from point A to point B. So you're not dissolving, like in Star Trek, and then reforming someplace else. We're simply transporting the information of every atom. So atom for atom, how much information is there in a human body? It is beyond imagination. It's 10 to the 25 or so. Okay, let's take another short commercial break. Welcome back to Science Fantastic with Professor Michio Kaku. Give us a call and perhaps you can have your thoughts heard on over 100 radio stations that carry Science Fantastic. Once again, give us a call. Okay, well, let's move right along now and go to the next listener phone call.
JJ, Navarre Beach, Florida. My question is, what will be happening with the polar shift? I hear sometimes in the middle of the night people are talking about the polar shift and when might it happen? What would be some of the results? Thank you so much.
Okay, interesting question. First of all, we have to differentiate two types of polar shifts. Believe it or not, there's not one, but two. First is the magnetic poles. The magnetic poles do move, and I'll explain how we know that in a minute. So that's one kind of pole shift. The other pole shift is the geologic North Pole, around which the Earth spins. Now, we do not expect a polar shift of the geologic axis of the planet Earth. If that were to happen, it would tear the Earth apart. That would be Armageddon. That would be a catastrophe beyond human imagination. We don't think that's going to happen. However, the magnetic poles do shift regularly. In fact, the magnetic field of the Earth is diminishing right now. Even as we speak, there's a slow diminishing of the strength of the Earth's magnetic field, which we can actually measure, meaning that in the coming millennia, it means that the magnetic field will probably go near to zero and then shift. And then perhaps the poles themselves will move. Now, first of all, we know this by simply digging into the lava flows of Hawaii. Go to Hawaii, dig into the ancient lava flows going back thousands of years underneath your feet. And when lava solidifies, it hardens the direction of the North Pole in the magnetic materials of the magma. So by simply digging into the crust of the Earth, digging into the lava flows, measuring the direction of the North Pole, you see that it shifts. It shifts as you go deeper and deeper into the lava flows. So we are going to be having another polar shift in the coming thousands of years, but don't worry about it. We're not talking about a geologic polar shift, which would destroy the Earth. We're talking about a magnetic shift, and that happens rather frequently, once every several thousand years, so I wouldn't worry too much about it. Okay, well, let's move right along to the next listener phone call.
John, calling from Waite Park, Minnesota. All of those ships that during the World War II that blew up in the Pacific, and all that oil and all that gasoline, and how much was actually along our shores on the East Coast, and also the H-bomb that was blown off in the Pacific, and of course in Japan and so on. How come what happened then has not affected us? So Mother Nature apparently has a way of being able to deal with this, and maybe the good doctor can talk about this. Thank you so very much.
Okay, well, some of my friends who actually study fallout and nuclear blasts and pollution, they like to quote the phrase, the solution to pollution is dilution, meaning that the Earth is very, very big. We are very, very small. And so even though we've exploded many hydrogen bombs and atomic bombs and released lots of radiation into the atmosphere, eventually it dilutes. But it's still there. It doesn't mean it disappeared totally. For example, if I get a Geiger counter and put it right next to your body, right now, take a Geiger counter, put it right next to your body, I can detect radiation from Chernobyl. I can detect radiation from 3 Mile Island, from Hiroshima, from Nagasaki. Believe it or not, yes, you contain in your body radioactive atoms that were detonated at Hiroshima, Nagasaki, but are they dangerous? No, and I'll explain why. Well, yeah, in some ways, The Northern Nature can heal itself and regenerate, but yeah, the radiation is still there. It just got diluted. So if I get a Geiger counter and put it next to your body, believe it or not, I can actually detect radiation. Radiation from Nagasaki, Hiroshima, Chernobyl, 3 Mile Island, Fukushima. Yes, your body still contains that radiation, but it's been diluted over such a large distance that it's not harmful. In fact, I still remember during the Chernobyl accident of 1986 that radiation from Chernobyl actually sailed over New York City, found in the milk. That's right. In fact, some mothers got very anxious and would email me and call me and stuff like that saying, what? Radiation from a Russian nuclear disaster sailing over New York City getting into my milk? Well, yeah, the answer is yes, but don't worry. Because of the dilution factor. It was so great coming from Russia, and the dilution was so great that it was basically harmless for the most part. But, yeah, the scars of it are still there. Okay, let's move right along to the next listener phone call.
Hello, my name is Lane. I'm calling from Overland Park, Kansas. Does antimatter have a negative mass, which causes a repulsive gravity? And if not, how do we know that? And if not, could there be negative mass particles and antiparticles which cause the repulsive gravity, which could account for both missing dark matter and the dark energy that accelerates galaxies apart? Thank you.
Wow. Well, the short answer is no, but let's break it down. First of all, antimatter is different from negative matter. Antimatter simply has opposite charge, but we think it has the same mass. So if I have a lump of antimatter, it would weigh just as much as a lump of matter. And if I dropped it to the floor, both would go to the floor, hit the floor at the same time. Now, we've never done this experiment. Antimatter is so rare, so expensive, that nobody has ever watched antimatter fall, believe it or not. However, every physicist that I know believes it will fall because of Einstein's theory. Einstein's theory includes antimatter, and therefore Einstein's theory predicts that antimatter should fall, not fall up, fall down. Have we ever done that? No. Now, there is something which may fall up, and that is called negative matter or negative energy that you referred to. We once thought that negative matter and negative energy simply could not exist. But now we know that's not quite true. It turns out that no one has ever seen negative matter that would fall up, not fall down. But negative energy does exist, and we've actually created it in the laboratory. And we think that could then cause dark matter and dark energy. So let me explain now. Dark energy is what makes the universe expand. It is anti-gravitational, therefore it pushes the galaxies apart, and that's why we have the bubble of our universe expanding because of anti-gravity. We think that it could be related to negative energy. In fact, there's a Nobel Prize waiting for anyone who can prove that what is causing the universe to expand is, in fact, negative energy. So at the present time, we simply don't know what is causing this expansion of the universe. So once again, antimatter, we know it exists. We make it in the laboratory. We have anti-atoms, for God's sake. In Geneva, Switzerland, they've been able to create antiprotons and anti-electrons, and anti-electrons circle around antiprotons, giving you anti-hydrogen. Now, does that mean that anti-people are possible? And the answer is yes. It would be very expensive to create anti-people, but anti-people are ordinary humans like us, except every single atom has opposite charge, so matter turns into antimatter. Is that possible? Yes. Is it practicable? It would simply bankrupt the planet Earth to create enough antimatter to create anti-people. Now, why are we curious, therefore, about negative energy? Two reasons. Negative energy does exist. We can make tiny, tiny quantities of it in the laboratory. We think that perhaps it has something to do with expansion of the universe. And second, if you have large quantities of it, you can build a time machine. That's right, a time machine. Okay, let's take another short commercial break. And after the break, we'll get right back to your listener phone calls. The lines are open. Okay, let's move right along now to the next listener phone call.
All right, hi. My name is Kazang. I'm listening to you streaming on the internet from New York City. My question is that aliens. My theory is that aliens may have actually, crashed a probe on Earth that was primitive, like from when they were first starting their interstellar space program. And I'm wondering why such things haven't been found, because the Starshot program, for example, would send small stamp-sized probes to the entire universe. So the aliens must have had something similar to that, or they may have had like a very primitive, like spacecraft, like from prehistoric times that may have been in the fossil record. Perhaps aliens also may have abducted the Tyrannosaurus Rex or its DNA, and may still, and theoretically, the T-Rex may still be alive on an alien planet. I'd like to know what your thoughts on this are, and what this means for the existence of extraterrestrials.
Well, that's a mouthful, but let's try to break it down. First of all, of course, science fiction movies love to explore the idea that ancient civilizations landed on the Earth thousands, millions of years ago, maybe even took some dinosaurs with them. If you remember the movie Forbidden Planet, which was done back in the 1950s, it said that the aliens, well, they landed on the Earth millions of years ago, and they even took animals with them from the early Earth. Well, first of all, yes, we can speculate, but it's speculation. We need proof. We need more than simply statements that, well, perhaps aliens could have landed on the Earth. Yes, perhaps there could be alien visitation. Yes, perhaps maybe in the fossil record there's evidence of this. Yes, all that is potentially true. But we need hard evidence. Now, some people point to Roswell of 1949 when either a weather balloon or a flying saucer crashed. But of course, that is a source of controversy, and the Air Force has its point of view, saying that it was a weather balloon, not an alien craft that landed in New Mexico. However, the defenders of the Roswell theory say that, well, why should we believe the military? They've been lying to us all these decades, so why should we believe them this time? Now, my personal attitude is that if one day you ever get abducted by an alien flying saucer, what should you do? For God's sake, steal something. I don't care what it is. An alien paperclip, an alien chip, an alien a pen. Steal anything, because that would end the debate right there, right then and there. Alien DNA, alien chip, alien technology, that would just end the debate right there. Otherwise, we have endless speculation, and speculation is cheap. You can either make up a story or perhaps something really did happen, but how do you prove it? And so, yes, you're absolutely right. Perhaps the aliens, when they first began to explore outer space, perhaps they crash landed on the Earth, perhaps they took some dinosaurs with them. All of that is possible. But hey, we want to go beyond simply speculation. We want some hard evidence. Otherwise, we could, in an afternoon, come up with all sorts of theories, none of which are provable. So again, steal something. The next time you're in a flying saucer, some piece of hard evidence is necessary to clinch the debate. Okay, let's move right along to the next listener phone call.
Michael, and I live in New Mexico. When a man holds his breath and dives very deep, like competition divers do, according to the pressure laws, his lungs should collapse. And the pressure at these really deep dives of 300 and 400 feet should crush his chest, but doesn't. Why is that? Thank you.
Well, you ask a very interesting question, because in principle, the weight of water could definitely crush your lungs, and there's a limit to how far the human body can go, even if you're trained since childhood to dive deep. Now, first of all, every square inch of your skin bears, atmospheric pressure bears down in every square inch of your skin to the tune of about 15 pounds. 15 pounds per square inch is the air pressure beating down on every square inch of your skin. Then the question is, why don't you collapse? Because you're in the middle of you're in the atmosphere of the Earth. You have 15 pounds of air sitting on top of every square inch of your skin. Why don't you collapse? And the answer is because you have 15 pounds on the inside pushing out. Now, some people find that hard to believe. You're telling me that I have 15 pounds per square inch on the inside of my body pushing out. Then how come I don't explode? Well, it's because the two 15 pounds per square inch balance each other. However, if you were to go into outer space, that removes all the air surrounding you, and you then have 15 pounds on the inside pushing out. And then what happens? You explode. You explode because in outer space there is no air to push down on you, so you have 15 pounds per square inch on the inside of your skin pushing out, and you blow up. We demonstrate that in our physics class. We have a vacuum chamber with a balloon, and we blow up the balloon, and then we slowly evacuate all the air inside the vacuum chamber. And what happens to the balloon? It gets bigger and bigger and bigger until it finally pops. So why do we have 15 pounds per square inch? Let's say I have a cylinder. A cylinder the size of a postage stamp in terms of its radius, and it extends all the way out to outer space. The question is, in that cylinder, very thin cylinder, how much air is there? Well, 15 pounds worth. That's why you have 15 pounds per square inch on top of your skin. Now, if you're at the bottom of the ocean, what is the weight of water pressure? Very simply, it is the weight of a cylinder of water beating down on every square inch of your skin. So how do they do it? Well, practice, practice, practice. Well, unfortunately, that's it for Science Fantastic.
Now, Science Fantastic with Professor Michio Kaku.
This is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And with us today is an astronomer who'll talk to us about the eclipse of the century. If you miss it, well, you may have to wait a few more decades for the next one. Yes, it was 40 years ago. 40 years ago in the United States that the people here had a chance to witness a total eclipse that crossed the continental United States. On August 21st, write that date down on your calendar. August 21st, you may have the opportunity to see a total eclipse of the sun. In fact, there are maps showing exactly where the shadow is going to cut across the continental United States. And even if you can't take a car ride or a plane ride to this narrow strip where you'll see the total eclipse of the sun, everybody will see a partial eclipse of the sun. But then the question is, how do you do it? You have to be careful because according to legend, Galileo himself burned his retina looking at the sun. In fact, according to legend, he eventually went blind in one eye. So the question is, how do you look at the sun? And just remember that solar eclipses are not forever. Millions of years from now, the moon is leaving us at the rate of about 1 inch a year, and it means that millions of years from now, we will not have a perfect coincidence when the moon and the sun apparently have the same size as seen from the planet Earth. So with us today is Professor Andrew Fracknoy, author of a children's book, When the Sun Goes Dark, and he's also convinced the Moore Foundation and Google to donate 2 million special eclipse glasses for free at local public libraries, because we don't want people to injure themselves looking at the eclipse of the century. Now, fortunately, if you missed this one, there's another one in 2024. That's quite rare. You have 2 opportunities to see a total eclipse of the sun. I remember seeing a partial eclipse of the sun right here in Manhattan, where I am right now. I got a pinhole camera. That is, I got an ordinary sheet of paper, pricked it with a pinhole, and put a second sheet of paper beneath it, and lo and behold, you could see the image, a pinhole image of the sun as it was being partially eclipsed by the moon. And once again, the difference between a solar eclipse and a lunar eclipse is as follows. A lunar eclipse is when the moon falls into the shadow of the Earth. They happen rather frequently, once every few months. A solar eclipse, especially a total solar eclipse, is extremely rare. Like I said, the last time was 40 years ago, and you'll have a chance to see this on August 21st. And already the networks, all the big TV shows, everyone's talking about having specials around the eclipse of August 21st, when the moon goes right in front of the sun, precisely blacking it out, giving us daytime where the sky turns totally dark. We'll also talk with us today with Dr. Fracknoy about the history of eclipses. It turns out that eclipses go back thousands of years into the past when ancient astronomers tried to make sense out of these celestial things happening in the night sky. What does it mean, the ancients thought, when the sun turns dark? And also, you may want to go to my website. My website is mkaku.org, mkaku.org. On Facebook, we have 3 million fans that follow my work. On Twitter, we have 500,000 fans. So let's take a short commercial break. And after the break, we're going to bring on astronomer Andrew Fracknoy, who will talk to us about solar eclipses, the solar eclipse of the century on Welcome back to Science Fantastic with Professor Michio Kaku. In this segment, we're going to talk about what some people call the event of the century. Don't miss it. The last time we had a total eclipse of this magnitude was 40 years ago. And if you miss it, well, you can probably wait a few more decades for the next one. So this is an event for the ages, they say, a total eclipse of the sun that'll go right across the continental United States. And with us today to talk about this event of the century is Professor Andrew Fracknoy. He's an award-winning astronomer, and he's a professor of astronomy at Foothill College in the Bay Area. And he's the author of a children's book on eclipses that we'll talk about, When the Sun Goes Dark. And also, he is part of Google and the Moores Foundation's effort to donate 2 million eclipse glasses for free at public libraries across the United States. And also, he's on the board of trustees of the SETI Institute, so we'll also say a few things about aliens from outer space as well. So, Andrew, glad you could be on Science Fantastic.
A pleasure being with you.
First question we always ask our guests is, how did you, as a youth, as a young boy, how did you first get interested in science?
Well, actually, I wasn't born in the United States, and when we came to America, I was 11 years old. And to learn English, I read lots of science fiction, comic books, and children's books, and just got fascinated by science fiction. And I remember at some point being in the library and suddenly realizing that exploring outer space wasn't just fiction. There was actually a profession where people went and did that for a living. They became astronomers. And I think from then on, I was set on my life path.
Okay. And tell us a little bit about some of the things you're doing. For example, the children's book, When the Sun Goes Dark. Tell us a little bit about that.
Well, so there is this eclipse coming up, as you mentioned, which is going to be visible not just to the people in the path of totality, but to 500 million people across North America as a partial eclipse, where the moon takes a big bite out of the sun as it covers part of it. And there's going to be lots and lots of families and kids wondering what's going on, hearing about it on the media. So my co-author, Dennis Schatz, and I wrote this book, When the Sun Goes Dark, as a way of explaining what's happening with the eclipse to kids. And part of what the story of the book does is it sets up a series of really simple at-home family activities that you can do to model an eclipse with a light bulb and a tennis ball, and to look at the way things go around the sky with hula hoops. And so we hope by reading this book either to their kids or with their kids, parents and grandparents can get the kids ready to be thinking about the wonderful science that's behind the eclipse.
Okay. Well, let's just jump right into the eclipse itself. First of all, why is this eclipse of the sun different from other ones? Because, of course, many people in the audience probably have seen partial eclipses of the sun. What's so different about this that's generating so much excitement?
Well, as you said, this is an eclipse that has the courtesy to go across the United States. We haven't had an eclipse that crossed the entire country since 1918. Being in the path of a total eclipse is very rare. We get eclipses like this regularly, but they can happen anywhere on Earth. And because 2/3 of the Earth's surface is water, often these eclipses are over some remote part of the world where only rich people can take a yacht to get there. And so here it's very nice and democratic that the eclipse is coming to the United States. Also, we think this is really the first eclipse over North America of the Internet age. And so lots more people will learn about it as they're learning through your show. And so I think there's going to be a lot more interest in the eclipse than we've ever had in an eclipse in North America.
So let's say you miss this eclipse. Let's say you're busy that day, or it's clouded over, or you simply have too many other things to do. How long do you have to wait for another eclipse like this, which is total, which crosses the continental United States?
Well, this is where we're very lucky. This is very rare, but there will be another total eclipse crossing the United States at a diagonal to this one, April 8th, 2024. So we get two of these all-American eclipses within a decade, which is really wonderful. And I'm sure the administration in Washington is going to take full credit for this once they realize it's happening.
Okay. Now, let's back up a bit. And first of all, explain to the audience, what is an eclipse? What's the difference between a lunar eclipse and a solar eclipse?
So an eclipse is when one body in the sky gets in front of another and blocks its light. In the case of a solar eclipse, we have the moon getting in front of the sun. And this, by the way, we should tell your listeners, is an amazing coincidence that as we look in the sky, the sun in the sky and the moon in the sky happen to be the same size. That's true from Earth, but not from other planets. Not from Mars, for example, is there. They have two moons, and the two moons are not the same size as the sun, and they can't lead to a total eclipse. So we're very lucky to have this. A lunar eclipse is much more common. That's when the Earth's shadow falls on the full moon, and so it's the Earth that gets between the moon and the sun. And that can be seen by many more people, and it happens much more commonly. These solar eclipses are much more rare, and we're very lucky to have one coming to our country on a nice summer Monday in August.
Okay, then the question is, how do you go about watching the solar eclipse? I mean, Galileo, the man who took a telescope and opened up the heavens for the first time for astronomers and the average person, didn't he have some bad luck looking at an eclipse of the sun, or looking at the sun and looking for sunspots?
Yes, so this is a big challenge because you know that looking at the sun is dangerous. You can really hurt your eyes by staring at the sun for any length of time. And yet here was Galileo trying to figure out how to observe the sun. And it was actually one of his graduate students, that we didn't call it that in those days, but one of his helpers who came up with the idea of projecting an image of the sun through his telescope so that the concentrated light didn't fall on his eyes, but on some screen further away, and then that reflected light was much more safe to look at. And so we'll talk about how to get safe eclipse glasses for the eclipse, but in the meantime, if you don't have those, you can do the same thing Galileo did and find a way to project an image of the sun and look at that image instead of the sun itself.
Now, according to lore, Galileo actually looked at the sun with a telescope directly, without filters, without any ways of diminishing the intensity of sunlight, and apparently he scarred his retina. And according to lore, he eventually went blind in one eye. Could you elaborate on that?
Well, I'm not really privy to what happened way back then, but we do get these reports that this was the first instance where someone made the big mistake of looking through an optical instrument at the sun. And we've been working very hard in this eclipse and other eclipses to warn the public, particularly if you have binoculars, if you have telescopes, you either need to get a safe filter, which is very securely attached to your binoculars or telescopes, and the experts will have these on August 21st, or you need to project an image of the sun so you don't suffer from the problem that you just described.
Okay, now some people are talking about pinhole cameras. This is a poor man's camera where you get a sheet of paper, prick it with a pinhole, and look at the image of the sun as it shines on a second sheet of paper. Could you elaborate on some of the methods that we can use to see the sun without burning your retina?
Yes, so this is exactly right. Let me start with what I think is the most fun one, is to make sure that when you go out to look at this eclipse on August 21st, you bring a colander with you. A colander, you know, one of those things that you use to wash vegetables or fruit, has lots and lots of pinholes in it. And if you hold the colander above your shoulder with your back to the sun, then the shadow that this colander makes on the sidewalk will show you lots and lots of these pinhole images of the eclipsed sun. And that's really fun to look at. It's a nice display, and then the colander can be a fashion accessory as well. So that's one way we're telling people. Another thing that you can do is to take a hand mirror, a compact mirror or a hand mirror, cover most of it with cardboard, leaving only a hole about a dime wide. And then use that covered mirror to get an image of the sun that you can reflect onto a wall or some other surface. And that reflected image of the sun will be bigger than a pinhole image and will be safe to look at. But as you say, having a pinhole projection, just making a pinhole in one piece of cardboard and then having a white sheet of paper some distance away also can show you a small image of the sun with a big bite taken out of it.
Okay, and what about the idea of simply getting an ordinary pair of sunglasses from a pharmacy or a neighborhood store? Do you have to be careful? Because, of course, there are different kinds of gradations of sunglasses. What about sunglasses?
Absolutely not. We can't warn our listeners enough that sunglasses are not enough, polarized glasses are not enough. If in the old days when we still had film photography, people talked about having dark negatives and using them to shade your eyes. None of those are safe to look at. Please don't use them. There are Eclipse glasses made of special mylar material, which cuts out a lot of the sun, and we'll talk later about how you can get one of those glasses. But just using sunglasses is really not enough. So especially if you have kids or you have a family, make sure you warn them about not relying on regular sunglasses.
Now, I would assume that the average person not knowing this will get, for example, an exposed photographic film or a piece of glass that's tinted and try to look at the sun through that, right? I mean, you're telling me that that's not the way to go, right?
That's right. And I think that's part of what we're doing. I'm on a national task force for the American Astronomical Society, and we've been trying to get the word out to the media. We have resolutions from various medical societies, and so I think there'll be a lot of warnings on the days and weeks before the eclipse for people not to do that. The only thing that does work in this way is welder's glass. If you know a welder or if you do welding for a hobby, a welder's glass or welder's glasses number 14 or higher are safe. But anything below number 14 is not okay. But again, the best thing is for you to try to get one of these inexpensive paper-framed mylar glasses called Eclipse viewing glasses. Those are the safest and I think the most fun to use on August 21st.
Okay, and you mentioned it before, but you're working with Google and the Moore Foundation to get them to donate 2 million Eclipse glasses for free at public libraries. So tell us a little bit about this effort that you're spearheading to donate 2 million glasses for free, and how can the average person listening to the show get one of these glasses?
Well, this has been very gratifying. We worried for a long time about how we were going to get these glasses distributed. They're not that expensive. It's just that we were going to have hundreds of millions of people who probably would like to have one. So we thought maybe a big company like Starbucks or Target would distribute them, but that didn't quite work out. And then we hit on this idea that there is already in each community across the United States an institution in the business of information distribution, and that's the local public library. So as you mentioned, we were very lucky to get the Gordon and Betty Moore Foundation and Google to donate 2 million Eclipse glasses. Now, by the way, we've just learned NASA's throwing in another 100,000 glasses for libraries. And these have been sent now to about 5,000 public
Okay, Andrew, unfortunately, we have to cut you off. We're going to take a short commercial break, and after the break, we're going to continue a discussion of the eclipse of the century. Plus, we'll say a few things about the history. Eclipses have a long, colorful history. We'll talk about that as well. Welcome back to Science Fantastic with Professor Michio Kaku. With us today is astronomer Professor Andrew Fracknoy, and we're talking about what some people call the eclipse of the century. For the first time in 40 years, the people of the United States can witness a spectacular total eclipse of the sun, and we think that hundreds of millions of people will be flocking to that band across the United States where you can see a total eclipse of the sun. With us today is Professor Andrew Fracknoy, Professor of Astronomy at Foothill College in the Bay Area, south of San Francisco. He's the author of a children's book, When the Sun Goes Dark, and also he's spearheading this program to get 2 million Eclipse glasses donated for free via public libraries. So let's say it one more time. What is the wrong way to see the solar eclipse of August 21st, and what is the correct way, and how do you get one of these eclipse glasses for free from a public library?
So let's be very clear. If you're lucky enough to be in the 60-mile wide zone, which stretches from Oregon to South Carolina, where you can see the completely total eclipse during the 2 minutes when the sun is completely covered by the moon, you don't need any kind of protection. Then it's perfectly safe to look at, and it's one of the most awe-inspiring and beautiful sights. But anytime that even a little piece of the sun is showing, if the sun is only partly eclipsed, which is what most of us will see throughout the United States and Canada and Mexico, then you need some kind of protection for your eyes. And sunglasses won't do it, darkened glass won't do it, Polaroid glasses won't do it. You need much better protection than that from the intense light of the sun. And as you said, one of the best things are these paper eclipse glasses with a special mylar plastic which cuts out most of the light of the sun. And we were very lucky, we were just talking about in the last segment, that we were able to get more than 2 million glasses donated. Ultimately, we think to 6,000 public libraries. We're getting another 1,000 or so involved in the next few weeks. And so most public libraries that are participating in this already have their glasses. So your first thought should be to ask your public library, are you part of this program to distribute eclipse glasses, and may I have a pair of glasses? Now, if it turns out that they've run out or that your library is not participating, there are 2 companies in the United States that make these glasses. One is called American Paper Optics. The other one is called Rainbow Symphony. And you can Google them and find out more about how you can get your own glasses. Also, many places will be selling them. I think Walmart is going to sell them. We know that most science museums in your community will sell them, and many colleges will have in the bookstore. these special glasses available. So if you call around your community, you might find a number of sources where you can get them. Probably best to get them early, because as more and more people wake up to the eclipse, there will be a great demand for these eclipse glasses.
Okay. And by the way, is there a website that people can dial into to find out more about your work and more about the solar eclipse and how to watch it safely?
Well, yes. So we're working with the nonprofit National Science Teachers Association. They published that children's book that you were nice enough to mention, When the Sun Goes Dark. And they've put online for free an 8-page booklet all about the eclipse, where it's going to be visible, in what way, what it's like in different cities, and various methods of watching eclipses safely. And that free booklet is available at the website NSTA.org. NSTA is National Science Teachers Association. So NSTA.org/solar science.
Tell us a little bit about the mythology of eclipses, starting with Mark Twain.
I will, but if I may, I just want to make sure that we give the correct web address, because NSTA.org by itself is not enough. It's got to be NSTA.org/solar science. The word solar science, all one word. That'll get you to the page where you can get that free 8-page booklet. But let me answer your question. Absolutely, the eclipses have been known. They were observed for a long, long time, going back into prehistory. And for most of history, they were very scary, because it looked like, to the ancients, some monster was coming and eating the sun, making it go dark in the middle of the day. And so people developed all kinds of legends about this, and they also developed a very clever solution. They said, if a monster is eating the sun, what we need to do is frighten that monster away. So in many countries, there was this long tradition that when you see an eclipse, you bring out pots and pans, and you bang them together really loud, making a huge noise in your village, and that will frighten the monster and will leave the sun alone. And you know what? It always worked. The sun eventually came back. And as you say, eclipses have inspired literature and music. Mark Twain, in the story The Connecticut Yankee in King Arthur's Court, had the modern protagonist know something about eclipses and therefore seem very powerful by predicting an eclipse that we already knew had happened back in time, but the people at the time were amazed that he could predict. And lots of things about eclipses. There are pieces of music. Carly Simon's song, You're So Vain, makes a reference to flying up to Nova Scotia in a private jet to view one of these eclipses. And that's really, I think, what's exciting about this eclipse is that unlike many eclipses where only rich people get to see it in some remote part of the world, here we're going to get everybody in the United States to see at least a partial eclipse of the sun.
Now, isn't it also true that because we know the precise date of these ancient eclipses, we can use that to date historical events and historical manuscripts? So if we have an ancient manuscript that refers to an eclipse, we can pretty much narrow it down, plus or minus 1 or 2 eclipses of when it happened, right? So can't we also use the eclipse as a way to date things?
Absolutely. So this has been, I think, one of the most remarkable successes of astronomy is that by understanding the motion of the solar system, the ballet which the planets dance in the sky, and the moon and the sun, as they move from Earth, appear to dance in the sky. By understanding this very precisely, we can not only predict when eclipses are going to happen in the future down to the minute, and you can find, by the way, tables of future eclipses and where they are on the web if you Google this. Not only can we predict them in the future, but we can go back in time, as you suggested, and find when all the eclipses of the past happened. And since eclipses were a big deal in history, we often find references to them in manuscripts, on tablets, and historical records. And so we can then use our understanding of when the eclipses happened to date events.
Okay. With us today is Professor Andrew Fracknoy, and he's also on the Board of Trustees of the SETI Institute. And a few weeks ago, we had Dr. Seth Shostak talk to us about aliens from outer space. So, first of all, do you believe that there are, in fact, alien civilizations out there that one day perhaps we can make contact with?
Well, of course, as you know, in science, belief is not the important thing, it's what the evidence is. But yes, based on the evidence, particularly the exciting news that I'm sure you've talked about on your show, that we are finding thousands of planets orbiting other stars now, that in the last 25 years this has changed dramatically in science, and we now know not only that there are families of planets around many stars, but even that there are Earth-like planets out there. This has made us, I think, a lot more optimistic that life on Earth isn't some unique thing, but that conditions elsewhere may be the same or similar enough so that life, and perhaps even intelligent life, could exist on many of these worlds.
And here's the killer question. Where are they? I mean, after all, they don't land on the White House lawn announcing their existence. Here we are, folks. They don't promise us advanced technology, blah, blah, blah. Hollywood, of course, has an whole industry around this. So the question is, if they're out there, then how come they don't land on the White House lawn?
Well, as you say, there is a whole industry. This is sometimes called Fermi's paradox or Fermi's question. And there are lots and lots of answers to this. But let me just tell you some of my thoughts about this. First of all, the stars are really far away, and it takes a long time to get there. So, for example, the fastest spaceship that the human species now has would take almost 70,000 years to get just to the nearest star. It's hard to find graduate students to volunteer for a trip like that, by the way. But in any case, this is something which probably makes travel either very slow or, if we want to go much faster, very, very expensive. And that's what makes us think that probably we're not going to make contact with aliens by traveling as much as by sending messages, just like we're communicating with the show's listeners at the speed of light using radio waves. And the information you get from the radio station that you're listening to your house or to your car almost instantly at that speed. In the same way, we think that species might communicate using waves that travel at the speed of light. And part of what we do at the SETI Institute is to search the sky for indications that some sort of intelligent signal might be coming from the stars.
Now, Dr. Shostak on the radio said something which kind of surprised me, but actually makes a lot of sense, something that I've thought about, and that is if they really are out there, alien civilizations, they could be thousands, millions of years ahead of us, in which case they may be partly robotic or cybernetic, in which case maybe they don't use radio at all. Maybe they have completely different criteria for life, because with a robotic body, you don't have to be on an Earth-like planet at all. You can be pretty much anywhere you want to be if you are a Superman and have an invulnerable robotic body. So what are your thoughts about the fact that maybe we've been barking up the wrong tree, thinking that they're just like us, when they could be very much different from us? What are your thoughts?
Absolutely, and it's very difficult to predict life as we don't know it, which is why we scientists tend to stick to life as we know it. But absolutely, that's correct. There may be civilizations so far in advance of us that they're really way beyond what kind of technology we're just starting to develop. On the other hand, there may be civilizations that are still not exactly at our level, but not that far advanced. Or there may be, my favorite scenarios, that there may be civilizations where their equivalent of seventh graders still do science fair projects. And you know how in a science fair project you often duplicate a science experiment from long ago. That's a big deal to you, but not the scientists. So my favorite scenario is that there's a seventh grader out there in some advanced civilization that is doing a project that is way better than anything we can do now, but because he's doing an old project, he's sending the kind of waves that we can still pick up. And it's one of these seventh grade science projects that the SETI Institute will find when it's searching either for radio waves or for laser signals from the stars.
Okay, also, it's the anniversary, 70th anniversary of the Roswell incident of 1947. Some people swear by the fact that the United States government recovered dead bodies of aliens from a crashed flying saucer. So I'm sure that you probably get lots and lots of photographs and testimonials claiming that they've been abducted by flying saucer people. What are your thoughts?
Well, so we now know exactly what happened in Roswell. There was a weather balloon that was part of a top-secret project to send balloons up to get the pressure waves of Russian nuclear tests. And one of those top-secret balloons crashed at Roswell and then was whisked out of sight. The name of the project was Project Mogul. You can Google it. And so we now know exactly what that crash was about. But you're right. Lots of people see lights in the sky, and they mistake them for aliens and alien spaceships. So far, we haven't had any spaceships come to Earth which have left behind a little picnic garbage or a piece of the ship that fell off that we can test in a laboratory and see that it's not made of earthly materials. So we're waiting for that. Nobody would be happier than astronomers if the aliens were coming here and ready to talk or to tell us more about the universe. But so far, we're waiting for the evidence.
Well, I'm afraid that's it for Science Fantastic for this segment. Our special guest today has been Professor Andrew Fracknoy of Foothill College in the Bay Area, south of San Francisco. His book for children is When the Sun Goes Dark. And once again, if you want to find out more about his work, go to nsta.org/solar science, and perhaps you can be one of the people with a special eclipse class to witness the event of the century. Okay, once again, this is Dr. Michio Kaku for Science Fantastic.
This is Science Fantastic. Now, Science Fantastic with Professor Michio Kaku.
This is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And in this hour, once again, we're going to throw the lines open because this hour is your hour. Okay, let's move right along to the first listener phone call.
Yeah, my name is John, calling from northeastern Tucson, Arizona. My question is in regards to magnetic propulsion systems, so to speak. Using magnetic propulsion system as a launch platform and why we haven't done that for orbital spacecraft, why we haven't done more on that side of things.
Okay, well, you're absolutely right. Some people have proposed what is called the electromagnetic railgun. So far, we use chemical explosions in the form of gunpowder in order to shoot projectiles to the moon and projectiles outside of guns. However, other people have proposed using railguns, which is almost like something from Buck Rogers. A railgun consists of two long metallic rails. On the rail, you put a projectile that straddles the two rails. You send a current surging through these two rails, and by Faraday's law and whatever, the object that you put on the rails straddling the two rails is accelerated as the charge moves along the rail. Now, these rail guns are so incredible that the air friction that the object encounters when it hits the air is enough to flatten it. When was the last time you saw air flatten metal? That's what happens because these rail guns move so fast. In fact, it's projected that the military will one day be able to launch satellites using rail guns from the planet Earth. I mean, this is wild. Think about this. Having a gun that can launch a satellite. No need for booster rockets, first stage, second stage booster rockets. No, a gun that can launch a projectile into outer space. Now, what's the catch? Well, there's always a catch someplace. First of all, the railgun accelerates an object almost instantaneously. Therefore, the G-forces are incredible. The G-forces are so great that it would flatten steel. So if you have an astronaut that's going to be blasted into outer space with a railgun, he will be flattened like a pancake because of the sudden surge of acceleration that takes place in a railgun. So in an ordinary rocket, the rocket accelerates rapidly, but it doesn't crush the astronauts. The astronauts only feel maybe 2 or 3 times the force of gravity. However, with a railgun, it's sufficient to flatten steel, let alone bone and human flesh. So who's interested in railguns? Well, obviously the military. The military has experimented with railguns. In fact, you can even build a railgun inside your own garage. I've seen high school students that have actually created railguns inside their garage. Now, of course, these railguns do not attain 18,000 miles per hour, which is the orbiting velocity of an object necessary to go into orbit. However, yes, even high school kids for a science fair project can build a railgun, which of course can accelerate pellets of steel at enormous velocities. So the military, of course, wants to have industrial quantities of electromagnetic pulses. And for them, yeah, what they want to do is to create a weapon that can be used. And again, the problem with railguns is that in some sense they are victims of their own success. They are so successful, they will flatten steel, making most projectiles impractical on a railgun. But again, that doesn't prevent the military from dreaming about the day when they may have Buck Rogers weapons. Now, obviously, if air pressure and friction is a problem with railguns, why not put them into outer space? In outer space, there is no air. There is no air friction that slows down or flattens steel. And then, of course, it would be quite possible to shoot objects almost instantly outside of a railgun to use as a weapon. So yes, the military has in fact looked at that possibility as well. Okay, let's move right along now to the next listener phone call.
My name is Norman. I'm calling from Anderson, Texas, and the radio station is WTAW. And my question is that if there is a consensus of scientists that agree on a certain scientific principle or theory, does that make it fact? Thank you.
Well, you ask a very interesting question that goes to the heart of science, and that is science done by a vote? Do scientists simply vote on something and they deem it to be correct? And the answer is no. Science is based on 3 things. It has to be testable, it has to be reproducible, and it has to be falsifiable. That's a criterion for science. And if somebody comes along, the next Einstein, and shows that the previous set of theories are wrong, then we have no choice but to adopt the new theory. That's why many people call scientists revolutionary conservatives. That for the most part, scientists are very conservative. They don't go by majority rule. They simply go by what is experimentally verified. However, if one experiment doesn't fit the data, if one experiment shows that the previous theory is wrong, then scientists become revolutionary, because you cannot argue with data, especially data that is reproducible, falsifiable, and testable. Now, let me give you an example. Just before the outbreak of World War II, Albert Einstein was famous even at that point, but the Nazis didn't like that. The Nazis called relativity Jewish physics. And so the Nazis assembled a book. It's a very famous book. The title, in German, read 100 Authorities Denounce Albert Einstein. In other words, they interviewed and took statements from 100 of German scientists, the cream of German scientists, to be put in a book denouncing the work of Albert Einstein. Well, the media went to Einstein himself, and they asked him, what do you think about the fact that 100 of your peers, 100 of the finest scientists that Germany can produce, have written a book denouncing your theory? And Einstein replied, you don't need 100 authorities. You need one fact. One simple fact would violate all the theory of relativity. But of course, nobody could create even one simple fact. Okay, well, let's move right along now to the next listener phone call.
Yes, hi, Professor Kaku. My name is Brian. How far out do you think we are until we will be able to have the technology to capture and record thoughts and dreams, both visually and audibly, and be able to play them back as you would any film or video or even something you see on YouTube?
Well, 5 years ago, if you were to ask that question on Science Fantastic, the response would have been, ha, humbug, come on, give me a break. No way. Well, times have changed. In fact, in my latest book, The Future of the Mind, I actually go through documentation by which one day we may be able to do exactly that. That is a Technicolor with sound videotape of the dream that you had the previous night. What I did was I went to Berkeley, where I got my PhD so many years ago. I visited the neurology laboratory there, and yes, they do it. They can actually begin to photograph thoughts. Here's how you do it. You put a subject in an MRI machine, which can calculate blood flow in 30,000 places in the human brain. That's how accurate MRI scans are today. They can actually calculate blood flow in 30,000 locations in the living brain. Now, where there's blood flow, there's electrical activity, because that means you're thinking. Therefore, second by second, you can actually see thoughts. Thoughts go ricocheting from one part of the brain to another part of the brain to another part of the brain. Then what they do is, when you're looking at a picture, the MRI scan of your brain is fed to a computer. The computer then analyzes blood flow in 30,000 dots and then, ta-da, prints out a picture of what you are thinking about. This is amazing. And if you fall asleep, the machine keeps on going and prints out a picture of what you are dreaming about. So I had a demonstration of this when I visited the laboratory myself, and I saw these pictures. First of all, I saw pictures of what you are looking at. If you're looking at an elephant, for example, by golly, the computer assembles a picture that roughly looks like an elephant. If you look at a human, yes, the computer will print out a picture that really does look like a person with head, eyes, nose. Now, when you go to sleep, it's much fuzzier, of course. However, it still prints out a picture. The pictures are not so spectacular, very, very fuzzy. But the very fact that I can even talk about this is amazing. Once considered preposterous, and now we do it in the laboratory at the University of California at Berkeley. Now, you mentioned sound. Sound would be a little bit more difficult because sounds are generated through the left part of your brain. The left brain generates sound. The back of the brain assembles visual images. However, we're going to get to the point where we can even begin to digest sound as well. We're not at that point yet, but as I said, we are at the point where even if you are dreaming, we're able to photograph the image of your dreams using computers. Now, this is a very fast-paced field, of course, as we begin to have what is called brain-computer interface. Telepathy is already possible by thinking certain thoughts. In the future, you'll be able to type. Think about that. Typing a document simply by thinking about it. This is almost within the realm of possibility today. And my colleague, Stephen Hawking, who is paralyzed, of course, the next time you see him on TV, look at his right glass. In his right glass, there's a chip. That chip picks up radio signals from his brain and then processes it and types messages. And so that's how Stephen Hawking communicates with the world today, by thinking and communicating through a computer. So in other words, in the future, we'll have BrainNet. We'll have images. We'll have sound, feelings, emotions, memories sent on the Internet. And if you want to know more about BrainNet, then get a copy of my latest book, The Future of the Mind, which hit #1 on the New York Times bestseller list. So this is a hot field. In fact, even Elon Musk, famous for Tesla Motors, famous for SpaceX, even Elon Musk recently bought a company that is at the forefront of brain-computer interface, BCI. So find out more about this and also about BrainNet by getting a copy of my latest book, The Future of the Mind. Okay, let's move right on to the next listener phone call.
This is Eric. I'm calling from Texas. Have scientists developed a strategy as to when the day comes we contact intelligent life, how we will do it? I mean, will it be verbal, written, or will it be through hieroglyphics or sign language? Thank you very much.
Well, you ask an interesting question, and the answer to the question is no. We scientists have still yet to come up with a uniform protocol and a uniform method by which to decode signals from outer space. But if you saw the movie Arrival, then you realize how difficult it is to do that. In the movie Arrival, the aliens land from outer space. They hover over our cities, and we're able to get into their spaceships where we meet them. They look like giant squids, in fact. And they give us sign language that looks like spherical blobs of ink, like a Rorschach chart. And linguists have to decipher these messages. Now, of course, this is a very clumsy way to do it. I would think that aliens from outer space are so advanced that they have already deciphered our language, and we don't have to use clumsy sign language, for God's sake, to communicate with them. They'll speak perfect Hollywood English, because they've been monitoring us. If they're that advanced, they've already deciphered our languages and can speak to us in any language they want. But you ask a different question. Is there unanimity with regards to the protocols, with regards to the way in which we decipher messages from outer space? And the answer is no. No protocols, no uniform way of deciphering messages. Now, to be fair, it's very difficult to decipher a message because these aliens may not look like us or even think like us. For example, think of a dog. Maybe these aliens are descended from intelligent dogs, in which case their mind is full of smells. If you were to brain scan a dog, you'd realize that dogs don't necessarily communicate with verbal signals. They communicate through smells, thousands of different smells swirling around their brain. Or think about it. If they're descended from intelligent bats or intelligent dolphins, they'll use sonar. They won't use sound at all. And bats, many of them are blind or have very poor eyesight. They won't even use visual signals. They'll use sonar in order to communicate, in order to convey messages. Or take a look at bees. Bees don't even use visible light. They use ultraviolet light in order to navigate, and they dance. The way they communicate is by dancing to locate, for example, a flower bed. So aliens from outer space may be much different than bats, dolphins, bees, much more different than dogs or cats, and therefore who knows how they will communicate with us. However, I personally believe that one day if we make contact with them, they'll be so advanced that they will have already mastered American English, just like in the movies. Okay, let's take a short commercial break. And once again, you are listening to Science Fantastic with Professor Michio Kaku. Fantastic with Professor Michio Kaku. The lines are open. That's right. Give us a call. Leave your name, call letters of the radio station you're listening to, and the city you're calling from. And perhaps your thoughts will be heard on over 100 radio stations that carry Science Fantastic. So give us a call. Well, let's move right on to the next listener phone call.
My name is Frank. I live in Pennsylvania. My question is the building blocks of the universe. The scientists always talk about them, but I'm wondering, did it take an intelligent creator to create the building blocks to build the universe? And if so, how could the creator create itself if there is nothing out there in the universe? Thank you.
Well, you are asking the $64,000 question for which there's no unanimity of response. However, let me try to break down your comments piece by piece. First of all, we do have the atomic theory. And the atomic theory allows us to create transistor radios and lasers and rocket ships and all sorts of wondrous chemical and physical devices that you see in your living room. Science without the atomic theory would be like going back to the Middle Ages when we had witchcraft and hocus pocus, right? However, then the question is, well, where did these atoms come from? Well, now we think that atoms are made out of something called quarks that make up the proton. 3 quarks make up a proton. Then the question is, well, where do the quarks come from? Well, we think they come from strings, tiny little vibrating strings. Each note on a vibrating string corresponds to a subatomic particle, and that's why we have so many subatomic particles. They're nothing but musical notes. So if string theory is correct, and it has not yet been verified experimentally, it means that physics is nothing but the harmonies of vibrating string. Chemistry is nothing but the melodies you can play on strings. The universe is an orchestra of strings, and the mind of God that Albert Einstein wrote about for the last 30 years of his life, would be cosmic music. Cosmic music resonating through 11-dimensional hyperspace. That would be the mind of God. But then the question is, as you ask, well, then where did God come from? And it goes on and on and on. Where did that come from? Where did that come from? Well, ultimately, we want to find what is called the God equation. That is an equation 1 inch long that, according to Einstein, would give us all known physical law. That's the theory of everything. The closest thing we have that today is string theory, but then some people ask the question, well, where did string theory come from? Did it come from intelligent design? Well, the short answer is we don't know, but let me tell you what Einstein thought about this. Einstein was asked the question, is there a God that gives us relativity and the quantum theory? And Einstein said, well, you got to be careful. There really are two kinds of God. First is the personal God, the God that smites the Philistines, the God that wipes out your enemies, the God that gives you that bicycle that you've always wanted for Christmas. Einstein did not believe in that God. He didn't believe that God that created the universe existed just so that we can smite our enemies and get bicycles for Christmas. No. He believed in the God of Spinoza, the God of Leibniz. That is the God of harmony, the God of beauty, simplicity, elegance. He believed that the universe was so beautiful that it could not have been an accident. It could not have been a byproduct of random events. The universe is not chaotic. The universe is not random. The universe is not messy. It's quite ordered. And so that's why Einstein thought there was a God. Not a personal God, but the God that gave us the original 1 inch equation, the God equation, that allowed us to give us the universe. So where did that equation come from? Well, it came from the God of Einstein. Okay, well, let's take another short commercial break. You are listening to Science Fantastic with Professor Michio Kaku. Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. Okay, let's move right along now to the next listener phone call.
Hi, this is Jared calling from Florida. I was wondering if you had any thoughts on I believe it's called the infinitesimal possibility. I might have that wrong, but it's the theory that if the Big Bang had happened at a fraction of 0.0000 going on for infinity with a 1 at the end, greater or smaller, that the Earth would not have happened. That the Big Bang was just so perfect we would not have existed had it been slightly different in any instance. And if that's the case, how could there possibly be life on another planet or anywhere else in the universe? Thanks for your thoughts.
Yes, you're asking what is called the anthropic problem, and that is the universe seems to be designed. That is, it seems as if it could not have been a pure accident. For example, the nuclear force, the gravitational force, they are just right to make possible life as we know it. For example, if the nuclear force were a little bit stronger, it would mean the sun would have burnt out billions of years ago, and the Earth wouldn't be here because the sun would have become a cinder. If the nuclear force were weaker, a little bit weaker, then the sun would never have ignited to begin with, and it would be all dark, and we wouldn't be here. And so the nuclear force is just right to make possible intelligent life. Also, take a look at gravity. If gravity were stronger, then we wouldn't have necessarily the Big Bang, but a big crunch. All the stars in the galaxies would have been crunched together if gravity were stronger. If gravity were weaker, the universe would have blown apart billions of years ago, and things would be cold, and the solar system wouldn't exist. So if gravity were weaker, the stars, the galaxies, would have flown apart billions of years ago. So gravity is just right to make possible life. Well, it goes on and on and on. How many Goldilocks zones are there that has to be just right to create life? It turns out there are many Goldilocks zones. So many, in fact, that some people have claimed, therefore God exists. God chose the universe to be just right from the sun, just right so that we have stars and galaxies. Otherwise, we wouldn't be here to talk about the problem. Now, what are the pros and cons about the anthropic principle? I was first introduced to this by my second grade teacher. I'll never forget, my second grade teacher came in one day and said that God so loved the earth that he put the earth just right from the sun, not too close when the oceans would boil, not too far when the oceans would freeze, but just right to have life. That's how much God loved the earth. Well, today we have discovered 4,000 planets where the planets are too close. They are too far from the mother sun. Very few of them are just right from the sun to have liquid oceans. In other words, the solution to that problem is, well, two solutions. One, maybe there is a God. Two, maybe there are lots of dead earths out there. So the answer to your question is there are two possible solutions to the anthropic problem. A, maybe there is a God. Maybe there is a designer that designed the nuclear force, designed gravity to be just right so we have stars, we have galaxies, and we have Earths. Or there are dead universes out there. Universes where the nuclear force never ignited the stars, where there are no stars. Or universes where there's a big crunch, where all the matter squeezes together and simply goes out of existence. Which is correct? Well, the first theory, as I said, is called the anthropic problem. The second theory is called the Copernican principle. The Copernican principle is the opposite of the anthropic principle. It simply says the universe is not special. The Earth is not special, said Copernicus, and the universe is not special at all. In other words, there are dead universes out there where the universe does not tolerate life as we know it. Now, which is correct? Well, these are two philosophies. They're not testable, because to test it, we would have to create alternate universes. But they're two philosophies, both of which are compatible with every single data point, every single experiment ever done in the history of astronomy. The anthropic principle, which says the universe is so special, maybe it was Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. That means you're not going to get a busy signal. That means you can call and have your thoughts heard on national radio. Okay, well, let's move right along now to the next listener phone call.
Hi, this is Jeff. I'm in Fairbanks, Alaska. I had a question about light. I've observed two intersecting shadows, and where they intersect, it's actually darker. How does that happen? I was wondering if you could expound on that. Thanks.
Yes, well, if you look at a shadow very carefully, you'll see that the shadow is not just pure black or pure white. The center of a shadow is darker than the outside. Why is that? Because of scattered light. Light, of course, moves in a straight line, but it ricochets, it bounces off things. And as a consequence, the rim or the outer layer, or the outer part of a shadow is dimmer than the center, which tends to be blacker. Therefore, if I put two shadows together, the intersection of two shadows is even darker than each shadow individually because of scattered light. Now, the question of shadows, as you mentioned, was also interesting because there's a conspiracy theory that says that we never went to the moon, that the moon program was faked by Hollywood, and to prove that, they say that our flag did not flutter like the movies show because there's no air on the moon. And second of all, the shadows. Not one set of shadows, but two sets of shadows. Obviously, shadows created by the lights of a Hollywood studio. So how do we scientists answer those two questions? Well, first of all, yes, the flag that flutters on the moon flutters as if there was air on the moon because there's tinfoil. The flags are made basically out of a tinfoil-like material, and that's why the flag seems to flutter even if there's no air on the moon. That's how we explain that. Second of all, what about the double shadows? Well, you have to realize that Earthshine is something that we're not accustomed to seeing. On the Earth, we have moonshine. At night, moonshine casts shadows. However, on outer space, in the moon, we have Earthshine. And so we have more than just one shadow on the moon. We have the shadow created by the sun and the shadow created by the Earth because there is Earthshine on the moon. Also, take a look at the fact that even North Korea, a country that's starving on the verge of collapse, can actually send satellites into orbit. So in other words, it's not such a big deal to go to the moon. So some people say it's impossible that we could go to the moon because it's so advanced. However, even North Korea can send an object in orbit around the Earth. So why did it take America to go to the moon? The problem is not going to the moon. The problem is coming back from the moon. That took the United States of America. Very few countries can get astronauts back from the moon safely. We did it. Now, to go to the moon is not so difficult. Quite a few nations have actually sent probes to the moon. In fact, the Chinese have sent probes to the moon, and in 2025, they want to have their astronauts put a flag on the moon, a Chinese flag on the moon by 2025. So going to the moon is not such a big problem. It's coming back. That's what America can do that very few other nations can accomplish. Okay, let's move right along now to the next listener phone call.
My name is Jim from Texas, and I'm wondering, when do we know too much?
Well, some people would say that maybe we already know too much. Well, as Einstein once said, our technology far exceeds our humanity. In other words, we have the technology. We know so much about the atom that we can split the atom and thereby destroy all life on the planet Earth. So that's our technology. Our humanity, however, has not liberated us. We still live with wars and famine and all sorts of disruptions of our environment. So here's an instance where our knowledge exceeds our humanity. So in some sense, we already know too much. Now look at it this way. Our personality hasn't changed much in 200,000 years since modern humans first emerged from Africa. You could take one of these cavemen from 200,000 years ago, give them a shave, put on some aftershave lotion, get them in a three-piece suit, and put them on Wall Street. And they'll look like all the other barbarians on Wall Street. We haven't changed that much in 200,000 years. But today, we have the internet. Today, we have nuclear weapons. Today, we have designer germs. Today, we have the capabilities of wiping out life on the planet Earth. But our personality hasn't changed much. For example, if there's a nuclear war and all central governments fall apart and we have food riots, humanity would degenerate into a bunch of barbarian tribes. Yes, strong men commandeering food and weapons would take us back a few thousand years into the past. So we humans like to think that we're so advanced, but in some sense we know so much without the humanity necessary to bind us together that one mistake and we could be sent back thousands of years into the past, back to the age of feudalism and warlords. Okay, well, let's take the next listener phone call.
Hi, this is John from Tampa. Dr. Kaku was talking about black holes, that instead of, I guess, the singularity forming into a dot, it turns into a ring. That it's possible that that could be a gateway, maybe from one universe to the next. And I guess my question is, okay, it's a gateway. Let's say a person falls into that ring. What happens to the matter of which he's made of? Is he going to be ripped apart and all that? Assuming he does, that is, the ring is a gateway. How is he spit out? Is he going to be the person, let's say, or is a rocket that's sent through there or a probe going to be the probe, or is it just going to be a bunch of mush?
Well, it turns out that as you approach a very large black hole, gravitational radiation and forces are not so great. The bigger the black hole, the weaker the gravity is as you enter the black hole, and therefore you will not be torn apart. In fact, it was mathematician Roy Kerr in 1963 who proved that mathematically, that if you have a spinning ring, you are not necessarily ripped apart, that you may actually go through the ring into a parallel universe without being ripped apart if the black hole is large enough. Okay, well, unfortunately, we have run out of time.